Okay, in this video we're going to do a pretty important chapter. Chapter 5 covers vectors and transformations, and it also covers a good deal about matrices. In fact, it has more about matrices than it has about anything else. So here's your little preview of what we're going to be doing. Okay, we are going to add vectors. So here's a vector A, and the way you add them is you start out with your initial vector, and then you do you take the tail of the second vector and put it on the head of the first vector. Okay, so this is a head, and this is a tail. So it's called a head-to-tail method. And then here is your resultant vector. Okay, we're going to be going over this in great detail. Okay, a vector has two attributes. It has direction and it has magnitude. Okay, so that's a little preview. So let's go ahead and get started. All right, we start talking about vectors as being oriented, so it should not be orientated, it should be oriented line segments. So an oriented line segment means that it has magnitude and direction. So this symbol above here looks like a ray, but for our purposes right now, it is a vector and not a ray. So the tail is located at P, and the head is located at Q. So this would be our vector. And this one's called PQ, so it must start at P and end at Q. Okay, things to note. If you change the order, it's going to be negative. So PQ, if PQ is positive, QP will go in the other direction. It'll have the same magnitude, but it'll be negative. So to set them equal, you'd have to negate the second one, and then they are equal. Okay, we start off by algebraically adding and subtracting vectors. So if I have vector A and I have vector B, then if I'm going to add them, I would add the first components, so 2 and a negative 3, which gives me a negative 1, and the second component. So these components are your x and y coefficients, or coordinate pairs. So 4 plus 5 gives me the 9. So it should be clear how we're getting this from the addition. So now let's go ahead and do the subtraction. So the subtraction is when you have a negative sign here, or when you flip these coordinates so that they are opposite signs. So, and we'll talk about that later on when we're drawing these vectors. So to subtract, I would say 2 minus a minus 3, that gives me the 5. And then 4 minus 5 gives me negative 1. Okay, so I have some more for you to practice down here. I know this is a little bit small and hard to see, but let's give it our best shot. So if we're going to add, this is vector A, I think this is A, and this is vector W, at least let's call them that, A and W. What do? I would say negative 7 plus 3, and negative 7 plus 3 is a negative 4, and then 12 plus 6 would be 18. So that would be the resultant addition of those two vectors. Okay, here are A and W, a little bit easier to see. I'm still doing addition. So negative 2 plus 1 gives me negative 1. And then 9 plus 1 gives me 10. So negative 1, 10 are the coordinates. And then here I have 9 and 12 and 1 and 9. And in this situation, I am subtracting the vectors. So it is, let's have it be the top one minus the bottom one. 9 minus 1 is 8, and 12 minus 9 is 3. Okay, here's another pair. Again, we're subtracting. Let's change that order. This looks like W minus A. So if that order is changed, we would start with W. Negative 3 minus a minus 4 will give me 1. Negative 6 minus a minus 3 will give me a negative 3. So you should have a good handle on how to do this algebraically. It is not that difficult to do as long as you are careful about your negative signs. Okay, in this slide, we start talking about how do we display vectors graphically, which will be very important. So this first vector, vector u, I have it drawn from the origin. When you draw from the origin, that's called standard form. Okay, so standard form indicates that the tail of the vector is at the origin. So if u is 4, 2, from the origin, you would go to the right on the x direction, 4, and then up 2, and then you would draw an what looked like a ray or a vector from the origin out through the point 4, 2. Okay, so that's standard form. This is another vector in the next picture right here. That is vector v. This vector is not drawn in the standard form. But what we're doing is we're going to start someplace on our coordinate plane. So, and then we're going to go up to or over to and up to from that spot. So that's what I've done here. So because these numbers are going by 2s, I'm starting here. This is my starting point, my non-standard starting point. I'm going to go up or over 2 to the right and up 2 to satisfy the xy pairing here, and that would be that vector. Okay, so this is vector w over here. This vector is not drawn in standard form, and that means it's not starting at the origin. The x and y components tell us that the head is 2 to the left and 4 up. Okay, so I'm going to have a starting point, and I'm going to go 2 to the left, -2, and then up 4, and that would be vector w. So this is just how you display your primary vector, the first vector, in your diagram. So let's continue on to the next slide, and we're going to be talking about the graphical addition of vectors. Okay, graphical addition of vectors is an important topic because it's very visual and it will help you verify what you have done algebraically. Okay, so let's start off, and we wish to solve the following. We want to add vector w to vector a. So neither one of these vectors is written in standard form, and that means that neither one of them starts at the origin. So if I want to graphically add these two vectors, what I'm going to do is I'm going to figure out which one's going to be stationary and which one I'm going to move. So I decided to keep vector w, so this vector is remaining stationary, and then to draw in vector a, what I'm going to do is I'm going to go to the head of vector w, and that's where the arrow head is, and I'm going to begin my sketch there from that point, and that point is 0, 6. From that point, I'm going to go over 2 in the x direction and on up 6. And that will satisfy the requirement to have a 2, 6 vector. Okay, so now I have the vectors, and they're written and they're drawn head to tail. Okay, so now I'm able just to draw a straight line connecting. What will I connect? I'm going to connect where I started. So connect where you start, which is right here, to where you finish, which is right here. Okay, when you connect those two, that is the summation. How do you get your x and y coordinates? Just the exact same way you did it when you did it algebraically. Okay, you can verify it. I can look at it and see that it's located at a place. It's going to be 0, 10. The fact that the x value is 0 means that it is a vertical line. Okay, that's an important insight right there. I got that 0 by saying 2 plus -2. But visually, I can see that I have a vertical line from my vector. Then the y component is going to be 6 plus 4. So I have a b equal to 0, 10. I just called that vector b. Okay, so that's the first page of graphical operations. That was addition. Let's go on and do subtraction on the next page. Okay, so we're going to start off with the same two vectors, vector w and vector a. And this time, I'm going to start out with W, and I'm going to subtract A away. So once again, I'm going to keep W stationary. Now, I see that the X and Y values of A are 2 and 6. But since I'm subtracting, I am going to go the opposite direction. So from the arrowhead of W, I'm going to not go to the right 2, but rather to the left 2. And then instead of going up 6, I'm going down 6. And that's because of the subtraction. All right, so I have my vector heading a different direction. It has the same magnitude, but a different direction. So now do the same procedure. Where you started is right here at the tail of W, and where you ended is at the head of A. Draw a line connecting those two, and that line's going to be a vector. That vector represents the subtraction of the two vectors. So let's see what we have when we do subtraction. Algebraically, I can see that if I said -2 minus, well, actually, as I write it this way, these already have negation put into it. So I'm just adding those numbers. So -2 and another -2 gives me -4. Then 4 minus 6 gives me -2. So see how these numbers right here, this is really -A. Okay, so that vector is -A. This vector is -A. This vector is +A. Notice the difference in direction. All right, so that's your subtraction. When you bring over the vector that you're going to subtract, look at the X and Y coordinates and do the opposite of what you see. So the definition of a zero vector is when you never actually draw the vector line. You start and end at the same spot. That is a zero vector. Okay, so this is not really going to come up in our work, but for completion's sake, I wanted to make sure that you had that definition. Okay, when one wants to find the length of a vector, that's also called the norm or the magnitude, we're going to use the distance formula, and that formula is similar to Pythagorean theorem, and we will talk more about that theorem a little later. But the formula itself, the distance formula, is the square root. So if I want to figure out the length of this vector from A to B, then I'm going to say A, so x1 minus x2, put that in parentheses and square it, plus this is going to be y1 minus y2 in parentheses and square it. That will be equal to your distance. Okay, we're going to explain how that's related to Pythagorean theorem, but for right now, we're going to tie it to the distance formula. That's how you get the norm or the length or magnitude of a vector. This is one symbol for that, and even just writing A, B next to each other with no notation, that's asking you to find the magnitude. So be aware of both notations as well as the wording of what is asking you to find the distance. Okay, in this slide, they're starting to make a connection between vectors and matrices, but they don't tell you that yet. So they're telling you that you can represent your vector instead of, like we've been doing it before, x comma y. Whoops, sorry about that. Let me back up. X comma y. You can instead write it like this. Okay, so this is also an ordered pair, but it's written in column formula. That column is actually a matrix. So if you're going to add vectors, and if you know your vector that's OA is x1, y1, and vector AB is x2, y2, this is how you add them. Nothing has changed except for the presentation. Okay, important things to know. This is very, very important. It's just kind of a little note off to the side, and the textbook doesn't go into great detail about this, but I'm going to tell you that if you're adding vectors, what's going to happen is, notice that if you add OP and then you add PQ to it, what happens? The P's kind of cancel, in your head anyway, and you get OQ. So then, let's just say, since we see that that's the relationship, what if I want to have an expression for PQ? Can't I use my one-step equation property and subtract away OP so that I can isolate PQ? Subtracting it away will give me just PQ. Okay, so I'm just going to point out this relationship one more time, and we'll get back to it. And when we do the activity for this chapter, this will come up a great deal. So actually, let me take 1 second. What if I said that you had OP, vector OP, and you added vector PT to it? Do you see that you would get, as a result, vector OT? Okay, because we're doing the head-to-tail method of addition. All right, so then I said to you, I will say to you, I'd like to have an expression for PT. So you would say, oh, I'm going to subtract OP from both sides. And therefore, my expression for PT, so the vector PT, would be taking what the values were for OT and subtracting away the values from OP. Okay, so that's what the main point is, that this head-to-tail method of addition allows you to know, because the P's will cancel, cancel in theory, it allows you to visually see what your resultant vector will be, and it'll be OT. Okay, here's another opportunity to practice some more vector addition using coordinates. So example A, if you let A equals 2, 5, and this is vector A, and vector B equals 1, 4, I'm sorry, this is 0.25, and from 0.25 you can build vector OA. So adding these two pieces together, after they become vectors, you get the following. So you're going to get 2 plus 1, so that's going to be 3, and then 5 plus 4, and that's going to be 9. So you will have a vector that has those x, y coordinates. Okay, again, example 2, you're going to do the same thing, only now you're going to do subtraction. So that means you're going to say 2 minus 1, and that's going to be 1, and then 5 minus 4 will also be 1. So that's a subtraction. So the first example was an addition, the second was a subtraction. So then I go on to say, one use of vector subtraction is to find the coordinate representation of a vector AB with tail A and head B. Okay, so we're going to play around with that. So here comes the little algebra we're doing on the previous slide. So from the definition of vector addition, we know that if I were to add OA to AB, I would end up with the vector OB. So if I want to figure out what the coordinates of AB are, I'm going to do this subtraction. I'm going to say OB minus OA. So what is that going to be? It's going to be, let's see, OA. So OA is 2, 5 minus OB, which is 1, 4. So you're going to end up having an answer of -1, -1. Now notice this. When let's see. Okay, so anyway, so this is what you end up with. And how did I get that? I used my knowledge of vector addition, knowing that since you're doing the head-to-tail method, you end up getting OB when you add OA and AB. Okay, one last thing I wanted to say. Do you see how when I did this subtraction, I got 1, 1? But when I reversed that subtraction, I ended up with reversed signs of the x and y. That's an important thing to note. So let's move on to the next slide. Okay, here's a little, just tiny little mini intro to matrices. They throw in scalar multiplication at the end of section 5.2. So scalar multiplication just means that you take this constant right here and multiply it by each term in here, and that's your result. And then I just wrote this as a little thing to remember. If you know the coordinates of AB, you also know the coordinates of BA. And since it's going the opposite direction, all you do is negate those coordinates. Since 0 is 0 is 0, you don't need to negate the 0, but you are negating the 3. So let's go on now to 5.3, which actually really hits matrices very hard. Okay, if you've never worked with matrices before, this is kind of a steep learning curve. If you have worked with them before, it's a pretty quick recalling curve. So I'm going to try to kind of cut it in the middle and give a pretty good introduction to what whole matrices are. And then you can certainly read the textbook as well. That gives you a little bit, another little insight. Okay, so a matrix is nothing but an array of numbers arranged as a rectangle. Okay, if the height of the rectangle is R, and the length is C, then the matrix is said to be an R by C matrix. So this is an R by C, and since they're both 2, it's a 2 by 2 matrix. So R equals row, and C equals column. Okay, this is a row. We have 2 of them. This is a column. We have 2 of them. Okay, the columns are vertical. Okay, so these little A's inside, and let me just erase all these lines in here. The little A's inside are each called elements. And when you want to write them generically, what you do is you write an A, and then you write the row and the column position. So A11 is located in row 1, column 1. A21 is located in row 2, column 1, and so on. Okay, so that's how that works. So you just call this little Aij is where you are open to plugging in whatever you want for rows and columns. Okay, if you have a pure row matrix, this is what it looks like. It consists of one row. Here is a pure column matrix. Column matrices are what we're using with our vector matrices. Okay, a zero matrix has nothing but zeros in it. A diagonal matrix has values on the diagonal, but nowhere else. Okay, a scalar matrix has the same value down the diagonal, and a unit matrix has ones down a diagonal. Okay, this is always also going to be an identity type matrix, but we'll get back to this. Our textbook does not go into a lot of this detail, but I wanted to give you a working knowledge of matrices as we go forward. So we have already done addition with matrices. We just didn't tell you were doing that. When we added our vectors when they were represented as columns, so if a vector was, say, 2, 3, and another one was 5, 6, and when you added those, you said 2 plus 5 and 3 plus 6, and you got 7, 9. That was matrix addition. So what if we have bigger matrices, that they're not just pure column matrices? So this is let's practice naming them. 3 by 2. So this is a 3 by 2 matrix, and this is another 3 by 2 matrix. You can only add 3 by 2 matrices to other 3 by 2 matrices. Okay, you can't mix and match on that. So what you're going to do is you're going to add every element, and they give you a pretty good explanation right there. And once again, it's not possible to add matrices that do not have the same order. Order meaning row times column, okay? It has to be exactly the same. How do you add two matrices together? If they both have the same dimensions, same number of rows and columns, then you just add up the numbers and you will have a final matrix of the exact same number of rows and columns. Okay, subtraction of matrices, the same exact thing. You have to have matrices that conform, so they have to have the same numbers of rows and columns. And you just subtract them just like we did with vector subtraction. Same exact procedure. Okay, here's scalar multiplication with matrices. We have done this before as well. So you have a constant in front of your matrix. It looks like this. You could first say, I want to do this operation, 2 times A, where A is a matrix. What you're going to do then is multiply every element in the matrix by 2. You can also work with negatives. So if you said you wanted to say -1 times matrix A, you would really just negate every term in matrix A, and that would be your resultant matrix. So this should be pretty basic now and pretty understandable by you at this point. Okay, matrix multiplication, so not scalar, but matrix times matrix can get a little complicated. So I have a pretty good slide here for you. And I put an important note here. So we've talked about this piece of it. Remember I said that if you're going to add or subtract matrices, they have to have the exact same dimensions in the same order. Well, that's not the case for multiplication. There's a different rule that has to apply. So you can take a 2 by 3 matrix and multiply it by a 3 by 2. And the result's going to be a 2 by 2. So see how the red have to be the same in the middle there? And the result is that they kind of cancel and you get a 2 by 2. Okay, you can take a 3 by 8 and multiply it by an 8 by 1. And the result's going to be a 3 by 1. Can you take a 2 by 4 and multiply it by a 2 by 4? The answer is no. You can't because the matrices do not conform. So the red in this situation has to equal the red. So let's try one. If I have a 1 by 7 matrix, I can multiply that by a 7 by anything matrix. Okay, so 7 by 5 would be good. If I multiply it by a 7 by 5, the end result will be a 1 by 5. Okay, how do we get this end result? So when you multiply a matrix, if you're going to multiply matrix 1, which is right here, times matrix 2, this is what you do. Row times column. And then you would say 1 times 1, right there, plus 1 times 2, right there, plus 1 times 3, right there. That will give you the new A11. So the new element in the first row, first column. Okay, now let's do the second multiplication. So to get your second element, you're going to multiply the red, so row by column. Okay, that will get you the second element. So 1 times 1, and then 1 times 2, and 1 times 3. And then we're going to keep going. Turn that green. This row by this column. When you finish that operation, we will have this entire thing done, and that is your top row of your matrix. Okay, that is the pattern we're going to follow for matrix multiplication. Okay, so it's really just an accounting system. You've got to be very careful to make sure that you are multiplying it just like I say. It is a good plan to write this step out, because then if you miss something, you can probably catch it a little easier than if you only have this step written out. So identity matrices we talked about a little bit. Identity matrices pretty much, give you back, your original matrix. So you have ones on the diagonal. And if you see when you multiply, this ends up giving you that term back. And then this ends up giving you this term back. All right, if you have a 3 by 3, you have ones on the diagonal. Identity matrices are just like multiplying by 1 in math. So this slide ends 5.3 in Chapter 5. So transposing matrices, that's a pretty easy thing to do. All you do is switch your row with your column. So if you see this capital T symbol, what they want you to do is to take this row and make it this column. Go down to the next row and make it the next column. And then go to the third row in this case, because we have a 3 by 3 matrix, and make it the third column. And that's called a transpose. Okay, so sometimes you have this kind of T, sometimes you have this kind of T, but the T always means transpose. So if you have, in this situation, we had a square matrix, which means that your rows and columns are the same. In this, you have 1, 2, 3, 4 by 2. When you transpose it, it becomes a 2 by 4. All right, so just be comfortable with that. And we'll continue these notes in the next video.